The following program is brought to you by Caltech.
So should we go ahead and get started? All right, so it's a great pleasure to introduce Yanbei Chen. And Yanbei is local here. He's a professor in PMA in physics and an expert about all things quantum measurement, interferometers, gravitational waves, that whole nexus of things. So Yanbei's trajectory, he finished his PhD with Kip Thorne here at Caltech in 2003. He did a one-year postdoc here at Caltech. And then he went on to the Max Planck Institute in Potsdam and in 2004. And he led a small junior research group there. And then in 2007, he came back to Caltech, and he's an associate professor now as of 2010. So anyway, without any further ado, on Yanbei.
Thank you. Does it work? Okay. Thank you, Keith. So today I will talk about the fundamentals of optical interferometry for gravitational wave detection. So my talk will be in three parts. First, I will briefly mention what is gravitational waves, some introduction. Then I'll talk about gravitational wave detection on the Earth. Actually, I'll talk a lot more about gravitational wave detections on the Earth than in space, because when I'm talking about ground-based detection, I also talk about how quantum enhancement can help us have better sensitivity. In space, it's not completely clear whether gravitational wave detection can be really helped by quantum, but I will try to, maybe trigger some thinking. So I'll start with gravitational waves. Briefly speaking, what are gravitational waves? If we have matter accelerating, they will actually cause oscillation in space-time curvature, and these oscillations will propagate. And that is, roughly speaking, gravitational waves. And then if there's some disturbance in the universe when they propagate to the Earth, normally it's going to be very weak perturbation of the Minkowski space-time around us. So if we put in a little more math, basically if we have a nearly flat space-time, we can write down the separation, in terms of a metric. And then the metric would then be the Minkowski metric plus a correction tensor. So basically, what does it mean? Well, this correction tensor, the trace reverse version of this correction tensor, if you put it into the so-called Lorentz gauge, it'll satisfy an equation that is almost like a wave equation. And then on the right-hand side, as a source term, it is the so-called stress-energy tensor. And what this stress-energy tensor has the time-time component, that is the energy density. The time-space component will be the momentum density, and the space-space components will be the stress that is in the region. So this is very much analogous to the electromagnetic field, where the vector potential is sourced by the 4-vector, which contains the current density, the charge density and the current density. So this is in a very weak field scenario, of course. So if we take this weak field scenario, and if we say that maybe we can do just like in the EM field, we can do a multipole expansion of the gravitational wave, then we find out, it turns out, basically the leading order of radiation turns out to be the mass quadrupole radiation. And the mass quadrupole radiation is proportional to the quadrupole moment double dot divided by the distance between the source and the field point. You can sort of see that this is the right kind of units, because the quadrupole moment is the mass of the system that is oscillating times the size of the system squared, and then the double dot is this whole thing times the frequency at which the oscillation goes. And also, by the way, L omega is just the velocity, the characteristic velocity of the system. And therefore, on the numerator, we just have the kinetic energy of that system. And in the denominator, it's just the distance away from that system. And because in relativity, we have G equal to C equal to 1, we basically have, V is just like some kind of order of dimensionless quantity Therefore, this h is dimensionless. It's roughly m over d times the velocity squared. And, and this h, at the end, what does it mean? It measures the relative change of the size of space and time, let's say, roughly speaking, in our coordinate system. We'll eventually know what it means. I'll show you exactly how does h influence matter and light. But basically, in terms of wave generation, we have this kinetic energy divided by a distance. But it looks interesting, but if you put in all the units, if you put in all the g's and c's, it turns out it's a very, very weak, small number. Just to give you an example, if you're 1 meter away from the hydrogen bomb that is most powerful ever tested, this is 2 times 10 to the 17 joule in terms of energy. And if you have this much energy in the kinetic energy, and you're 1 meter away from that bomb, you can measure 10 to the minus 27 in terms of the h, which is the relative change in space and time. So it's very, very tiny. Obviously, if you want to do this on the Earth, it's very, very difficult. But fortunately, we have astronomical phenomena. If we think about, there are very extreme processes that are happening in the universe. For example, if we have some kind of 5 solar mass object somehow accelerated to nearly the speed of light, maybe some fraction, then if we take this kinetic energy, and if this amount of energy is radiated in gravitational waves in the Virgo cluster, which is kind of the closest galaxy cluster near us, then we can have an h that is 3 times 10 to the minus 21. That is much, much larger than this. As it turns out, our precision measurement technology these days are able to measure this kind of strain, this kind of h. So that kind of starts with, about the indirect evidence of gravitational waves. So this has been mentioned by the previous talk. Basically, the direct evidence of gravitational wave, indirect evidence, come from this binary pulsar that was discovered in 1974. So a binary pulsar is basically 2 neutron stars, and then at least one of them is emitting radio pulses toward the Earth. So we can see this, but then through the modulation of this radio pulse, we can see that this neutron star is in the binary, and then for this particular pulsar that was discovered by these 2 guys, the orbital period is 7.75 hours. And then people actually measured through the relativistic corrections to the orbit. People actually calculated the masses and the orbital parameters of this binary. And they actually calculated how much energy is going to be carried away by gravitational waves in terms of quadrupole radiation. And then if energy is carried away by quadrupole radiation, when the orbital energy of a Keplerian binary decreases, the orbit will tend to shrink, and the orbital frequency will tend to increase, and the orbital period would also decrease. And then people did actually measure that change. So, of course, currently the gravitational wave frequency is very, very low. It's twice the orbital frequency, it turns out. It's 71 microhertz. And then people did measure over the scale now 30 years, and they compared the prediction of general relativity with the actual change in the orbital period, and it agrees very well. So it's not only evidence for gravitational waves, it's also a very good test of general relativity. For example, it'll be testing against dipole or monopole radiations. But the problem is, as it turns out, at the current frequency, the frequency is very low. As I'll talk about, this is a very low frequency that is not perhaps accessible to us very easily. And the other thing is that at this low frequency, the amplitude of the gravitational wave is also very weak. But as calculation goes, in 300 million years, this binary would actually have the orbit shrink to the stage where they will start go around each other at 5 hertz, and then the wave would be like 10 hertz. And then in a few minutes after that, the frequency will go up to kilohertz, and the 2 neutron stars will collide with each other. That would be very dramatic, because as it turns out, this will be the frequency band that we'll be aiming at on the Earth for detecting gravitational waves. But then the problem is, we only know a handful of such objects in our galaxy, and then they, merge in the scale of 100 million years. So that means that on average, on the average of 100 million years, perhaps, the estimation is like from, in the Milky Way galaxy, there could be 20 to, 1,000, but that's like the very optimistic estimates of such merger events happening in our own galaxy. So the message is, if we're able to go see a lot more galaxies far away distance, then we might be able to catch such events if there are such binaries that will eventually merge in other galaxies. So basically, then that introduces me to talking about sources of gravitational waves. Basically, the two neutron stars we talked about are going to be belonging to this high frequency category of gravitational waves. So these are basically at a frequency band of above 1 hertz and below 10 kilohertz. The 10 kilohertz is basically set by the scale of the masses of such systems, which will be the scale of solar masses. And then this 1 hertz is pretty much artificially set because on the ground, perhaps I'll talk about, it's very difficult to measure frequencies below 1 hertz. So these sources contain, for example, neutron star binaries or binaries containing neutron stars or black holes, or rotating neutron stars where the neutron stars are not completely spherical, or maybe collapsing stars, etc. So some of the real important reasons why we want to detect these waves is, for example, because we want to understand the structure of neutron stars. And also we want to know the details of black holes, not only that they're just very compact and very heavy, but exactly what is the space-time structure of a black hole and what space-time structure of binary black holes when they collide. On the other hand, there's another population of gravitational wave sources in the lower frequencies. So a lot of these dots, for example, they are in this frequency scale because they're all involving black holes of 10 to the 6 solar masses or 10 to the 5 solar masses. These are the typical masses of the black holes in the centers of galaxies. And therefore, they set these kind of scales. And therefore, naturally, we want to probe, we want to set up interferometers to detect waves that are at, for example, 10 millihertz. And then we will be able to probe the mergers of these black holes in the center of the galaxies. And then not only will we be able to have very high signal-to-noise ratios for detecting these gravitational waves, we'll also be able to understand, for example, how often and in what kind of states are these black holes merging with each other, because these will be black holes in the centers of galaxies. So let me then start talking about ground-based detectors. So I will basically talk about optical interferometry, the fundamentals of that. And then I will talk about how quantum mechanics and how quantum, well, essentially because our sensitivity could be mostly limited by quantum noise. And then techniques of quantum optics can help us improve our sensitivity. And then I'll talk about limitations of gravitational detection on the ground. So let me, before doing this, we have only said that h sort of measures the change of the size of space and time, but it's very imprecise. What we really need to know is to say in what sense does this h modifies the motion of mass and light. So here, let's be more specific. All through my talk, we'll be considering a wave that is a plane wave along a z direction. And then it turns out there's a coordinate system in which we can write down the metric perturbation in a very simple way. And for this z wave, the metric correction only has spatial components. It only has x and y corrections. And therefore, it's completely transverse, because x and y are transverse to the direction along which the wave propagates. And along x, and y direction, the h is opposite. And therefore, this matrix is also trace-free. On the other hand, the xy components are symmetric because this has to be a symmetric matrix. And therefore, this coordinate system is called the TT gauge. And this plus and cross functions, which are functions of t minus z because that's the wave propagation, These are called the two polarizations of the plane gravitational wave. So let's remember these two H plus and H cross as the two polarizations of the wave amplitude. But we're not going to use that previous coordinate system. We're going to go to the so-called local Lorentz frame around some kind of central object that I'm considering in the region that I'm spatial region. As it turns out, if I go to the local Lorentz frame, I can write down, basically I can describe the motion of matter as they're all feeling a tidal gravity field. Basically, for any object whose location is at x, the mass times the acceleration is equal to 1/2 the mass times this thing, which is just the H matrix times the location, plus any other non-gravitational force. And therefore, the effective gravitational wave is just like a tidal force. The word tidal basically means the farther away you are from the center, the bigger the force you're feeling. And of course, it's gravity because it's proportional to mass. The force is proportional to mass. So if you actually have free masses, an array of free masses, then you can integrate these equations because you can eliminate the non-gravitational force. What you get is the change of the location of the object due to gravitational wave is equal to, there's a 1/2, which I forgot. It's a 1/2 hjk tt times x of k. So what that means is that now literally this h, 1/2 h, is the deformation, is the strain with which these array of masses are going to deform. If we have H plus here, the plus polarization, and if H plus indeed is positive, then it means along the x direction things are going to stretch, then along y direction things are going to squeeze. But of course, if it is oscillating, then this pattern is going to oscillate. On the other hand, the other polarization basically means that matter on the 45-degree rotated axes are going to be stretching and squeezing. And well, the reason why we went to the local Lorentz frame of the center of these objects is that it turns out if the region has a size that is much less than the gravitational wavelength, which we will see will be true for ground-based detectors, it turns out light propagation in this coordinate system is not affected by gravitational waves. So we're only left with a force field that is just a classical force field. So then we can just forget about gravitational waves, and we can say that our problem now is just redefined as measuring a classical force field that is due to gravitational waves. And then we can just apply all the tools we have for measuring this force field. But of course, the one thing that we have to remember is that the field, as much as we can, we should make the separation of these objects far away, because then the displacement is proportional to the initial separation times the gravitational wavelength, or gravitational wave amplitude. So then it comes to the setup of a ground-based detector. Here I'm already using this a figure from the website of the LIGO website, and the LIGO means Laser Interferometer Gravitational Wave Observatory. So here is a schematic plot of this Michelson interferometer, because you see this squeezing, stretching pattern. Obviously, you think about Michelson interferometers that match this pattern. So for example, if we really have the z-axis, like the wave propagating along the z-axis, and this is in the xy plane, what we have then is, if we think about this as the center, and if our arm length is 4 kilometers, then it turns out as long as we consider waves that are below a few kilohertz, we're always fine. We're within the region where the size of the detector is much less than the wavelength of the gravitational wave, as long as we're below a few kilohertz, below 10 kilohertz, let's say. And that's the frequency we're aiming at in the LIGO detector. So, and then let's think about how the gravitational wave works in this case. So basically, the light will drive the common mode. So this is set up in such a way that let's imagine the light drives the common mode of the interferometer. So here you have arm cavities, but that's just trying to enhance the amount of power in the arms. Let's say this arm is on resonance with this light, so the light pumps here, and then there's just stronger resonant light in the cavity. And let's now say that we have a gravitational wave as marked by these arrows. So basically, these arms stretches and these arms squeeze. So what exactly happens is these two far mirrors will move. All these near mirrors, they're not going to move because the motion is relative to the motion is proportional to the distance away from the center. So these far mirror will move closer, this will move farther away. So the arm length is going to be modified by the gravitational wave. And then when that happens, the length of the cavities are going to be different. And then that difference is going to cause a signal light to come out from this port, which used to have nothing coming out. So that's the idealized version. So then you would have a signal light that is proportional to the strain of the gravitational wave. Of course, if you have a photodetector here right now to see that signal light, you're going to see something completely quadratic in the signal. So what you do is you have to impose a local oscillator light. So in reality, what happens in LIGO right now is that there's a small offset that is done into one of these cavities in such a way that there's already a phase shift, so that there's already a little bit of light coming out from the dark port, even when there's no gravitational waves. So this setup is like this following picture. Like the intensity of light here depends on the phase shift. When phase shift between the two arms are 0, you have completely 0, and there's no power, but then you're just a little bit offset here, So the reason why you only be a little bit offset here is that the laser noise of this laser will still pretty much cancel out from here. It doesn't really come out with a big fraction. It's only a tiny little bit of laser noise coming out. And then some of this carrier light comes out as a local oscillator. Therefore, this suppresses the laser noise. So you have to come out not too much. If it comes out too much, laser noise is bad. If it comes out too little, of course, you have other noises here. So you have to sort of find out the right amplitude for local oscillator. That is so-called the DC readout scheme. But for purposes of understanding of the fundamentals, we can just think about this as H as just the differential signal, and this local oscillator has no noise, and this is beating with that H, and then detecting our signal. So this LIGO detector actually, there are two such sites. And then there's one in Livingston, Louisiana, and the other in Hanford, Washington, and they're like 3,000 kilometers apart. And also the arms are chosen in such a way that they're as parallel as possible, but they're on the surface of the Earth, so they cannot be completely parallel. So this separation allows a little bit of localization, triangulation, but since you only have two detectors, you cannot completely localize on the sky. And then the pictures of these two sites are interesting, that they're exactly the same in terms of the instrument. They're almost the same in terms of the 4-kilometer interferometer is exactly the same, but then outside it looks kind of different. So it turns out there used to be two detectors in Hanford, Washington, but then it could be that in the near future that one set of these interferometers could be shipped to India to build another interferometer, but that's not completely decided yet. So in fact, in the entire world, there's not only the LIGO detectors, but there's a global network of detectors. And there are, in Europe, there's the Virgo detector and the GO600 detector. Virgo detector is 3 kilometer in arm length, is comparable to LIGO detector. The GO600 is 600 meters long, so it's somewhat shorter. And in Japan, there is a 300 meter detector called Tama 300, but they're building a new detector called Kagura in the Kamioka mine, which is also 3 kilometers long, arm length. And this is the LIGO India that I mentioned. So basically, right now, LIGO, there's LIGO and Virgo and Geo and Tama detectors, and Kagura would be in construction, and LIGO India is being planned. So in terms of the history of LIGO operation and the level of sensitivity, LIGO has started science runs since 2002, and you can see that during these science runs, the sensitivity still is improving between the different runs. And eventually from S1 to S5, the fifth science run, the sensitivity is in this purple curve, and it sort of matches the black curve, which is the initial design curve. It's called the science requirement sensitivity. So, and then after 2007, there were also improvements done to the LIGO detector such that it even has better sensitivity than the design requirement. And that's called Enhanced LIGO detector. But the aim of today's talk is actually to show that the level of sensitivity of these detectors turns out to be, in terms of spectral density, is 2 times 10 to the minus 23 per root hertz at around 100 to 300 hertz. So this is the level of sensitivity. If you still remember, I showed the Virgo cluster object amplitude of gravitational wave. That was 10 to the minus 27. So this shows you that this can even, this is actually can even see an event that is less dramatic than the one I was talking about. So, and here the spectral density represents such a quantity that is noise per unit power. And here I'm showing the square root of the spectral density, and it's related to the RMS noise in this way. So, and then I will go on to start talk about the sensitivity, how roughly with optical interferometry can you reach such a sensitivity. So it's basically, in terms of just the optics, it's a straightforward kind of exercise. So what you find out is that if you have a Michelson interferometer, it's essentially that you have this light, and then in the two arms, it goes through different phase shift, and then you're just comparing the phase shift between these two beams of light. And the phase shift is sort of 2 pi over lambda times LH, because 1/2 LH is the distance. And then the question is, what is the H that is measurable? And the H that is measurable, of course, is lambda over 2 pi L, and then divided by the number of photons available to you during the time of your measurement. Lambda over 2 pi L is just the typical scale, right? So, and this thing at the end is the light power times the duration divided by the photon's energy. So this is fairly easy to estimate. And then what you find out is that because the RMS noise is related in this way to the duration of your measurement, you actually have a constant spectral density because this delta H is 1 over square root of time, means your noise is a white noise. So your noise spectrum is just lambda over 2 pi L times this square root of H omega 0 over I. And this gives you 10 to the 20 per root hertz. So this is 4 kilometer, this 5 watt is sort of maybe the LIGO optical power. So this is still factor of 300 away from the LIGO sensitivity, but not that far. So then you can think about the reason why there's arm cavity and there's the so-called power recycling cavity there in front of the LIGO mirror. So the reason that you have these nested cavities is that you always make the cavities on resonance. So therefore, the power here is bigger than the power here, and the power here is bigger than the power here. And the way to think about it is that there are twofold kind of amplification. The first one is fairly easy. This power should just be the power in the previous page we should have plugged in, which is the input power in front of the Michelson. So it turns out for LIGO, this is 50 to 60 times, and then you get a square root of this number in terms of the sensitivity improvement, square root of the power, square root of this one. And then the arm cavity is a little more tricky because the arm cavity, there's two things in the arm cavity, in the cavity. One thing is how many times does light bounce in the cavity, and the other is what is the storage time of light in the cavity. So it turns out the light bounces 40 times in the cavity. And it turns out if for this cavity, for frequencies below the so-called bandwidth of the cavity, the 40 bounces is just the 40 times of improvement in amplitude sensitivity. So therefore, the naive picture on the right-hand side is the following. It's saying that you take the square root of this number, then you take 40 and you multiply, you get roughly 300, and that is the amplification, naive amplification. But the problem is because the light bounces many times in the arm cavity, if the gravitational wave frequency is too high and the gravitational wave period is too short, if during the storage time of the light in the cavity, your gravitational wave changes sign, oscillates too fast, then you don't gain sensitivity anymore. And therefore, when frequency of gravitational wave is too fast, you start lose sensitivity at this knee frequency, which is comparable to the light storage rate, light decay rate from the cavity, or 1 over the light storage time in the cavity. So I won't bother you with these formulas, but basically that turns out to be the gain factor. You gain this 2 over t due to the number of bounces, but then you gain this factor that depends on frequency, where you have a gamma, which is the knee frequency of your gain, which then this gamma is related with, is equal to this one, which is just 1 over the storage time of light in the cavity. So therefore, you pretty much understand this noise. And this is basically the photon counting noise. So this is just called the shot noise in your interferometer. It's due to the discreteness of photons, right? We have 1 over square root of n. So the other maybe complementary noise to that is the fact that these photons actually kick on the mirrors because, for each photon, you have this kind of momentum, and then when the photon is reflected, you kick on the mirror. On the other hand, the number of photons is fluctuating during any duration of time, and that noisy kick is going to give you another noise. So here I won't go into the details, but what I will show you is that radiation pressure noise, as it turns out, it just scales the opposite way from the shot noise, from the counting photon, the other sensing photon counting noise, called shot noise. So basically, when you so this blue curve is this curve that I talked about first, which is just due to not enough number of photons. The more power you have, the lower the shot noise. It goes like 1 over the square root of power. On the other hand, the red noise is the radiation pressure noise, where the higher the power, the higher the radiation pressure noise. And together, if you actually plot the total, if you sum up the noise spectrum, and you carefully plot the envelope of the total noise, you find out that the noise is bounded by the so-called standard quantum limit. And the standard quantum limit turns out to be given by a number that is quantity formula that is not dependent on the details of your laser interferometer. It only depends on the mass of your mirror, the h bar, and the length of the arm. So basically, this has to do with the fact that on the one hand, your shot noise measures how well you measure the mirror. Your radiation pressure noise measures, when you actually measure this mirror so carefully, you're actually imposing quantum mechanical back action into the mirror. And therefore, together, the total noise is subject to this so-called standard quantum limit, which only depends on the fundamental constants of quantum mechanics. So now, this is kind of interesting. I will mention a little more about this standard quantum limit. It turns out we will have to surpass the standard quantum limit to some degree in order to improve our detector beyond maybe the next generation. So that comes about in the section of quantum improvements. So basically, if we put this noise right now into the context of what is these quantum optical fluctuations, we have the shot noise and the radiation pressure noise that I mentioned. And these two kinds of noise, the shot noise is a dominant noise in the first generation LIGO sensitivity. But then there are other noise sources that actually dominate at lower frequencies, so the radiation pressure noise and the standard quantum limit do not yet show up in the first generation that has been completed. So, and these other noises concern, the thermal fluctuations. For example, this test mass internal thermal noise means that the thermal fluctuation in the shape of this mirror and in the thickness of this coating material. And the suspension thermal noise, basically concerns the fluctuation in the suspension system, maybe in the suspension point here, maybe in the fiber here. And the seismic noise is basically the vibration here, coupling down to the mirror. But I will not focus on those noise. I will focus on the more fundamental and optical originating noise. So now, in the second generation, what we will do, the gravitational wave community will try to actually push down all these thermal noise and seismic noises, so that at the end, even though the first generation detector, for example, the first generation detector that has been completed here is far away from the standard quantum limit, the second generation detector, which is advanced LIGO, which is now being installed and perhaps will start operating in 2015, maybe soon have detection. This is actually fairly close to the standard quantum limit that correspond to the 40 kilogram mirrors that it has. And then the community is planning third generation detectors, and these detectors would then, we will actually have much better sensitivity, but then they may have to really go beyond the standard quantum limit. So therefore, I will try to talk about quantum enhancements that actually will be implemented in these upgrades of gravitational wave detectors. So just to talk about the basics, we have, just to talk about perhaps describing quantum, in order to describe the quantum modifications a little more better, let's separate the electric field, or maybe the optical field in general, into quadrature fields, basically E1 cosine times E2 sine t. And these omega 0 is supposed to be the carrier frequency in the experiment, and these E1, E2 are supposed to be slowly varying. And then in the phasor diagram, we can plot the E1, E2 in different axes. And the way it goes is that if you have a carrier field along this phase, then E1 would be the amplitude quadrature, and E2 will be the phase quadrature, because these are amplitude and phase modulations. On the other hand, you can have different carrier phase, and then E1 and E2 would actually have different meanings, because you have different combinations of these E1 and E2s as amplitude and phase modulations. So, and therefore, these quadrature fields can be quite flexible. So, by the way, just because we're showing this, it's also, in principle, if we have any quadrature field in some optical, propagating in some direction, if we superimpose a carrier with a phase phi, then the amplitude quadrature of that particular carrier would then be modulating the amplitude of that light. And then if you have a photodetector there, you'll be detecting that particular combination, and that will make a Homodyne detection of this particular quadrature. If we take this quadrature picture, it turns out as we quantize the quadrature fields, these quadrature fields are much like displacement and momentum of mechanical resonators, mechanical oscillators. And the difference is that E1 and E2 actually are fields, and they each oscillate at all different frequencies. And at each frequency, E1 and E2 satisfy this Heisenberg uncertainty principle in the frequency domain. And then there are different quantum states that we can have. For example, the vacuum state would have the same amount of fluctuation between E1 and E2. And then the coherent field will basically can be viewed as a classical carrier light superimposed with a vacuum fluctuation. And then a squeezed state will be those where E1, E2 have actually the same area, but then different shapes of noise ellipses. And then if you superimpose these with a carrier, then you have here you have a phase squeeze state, and here you have an amplitude squeeze state, because this state has a very small phase fluctuation, and this has a very small amplitude fluctuation. And then in the same way. So let's come back and talk about quantum fluctuations again, and let's just first be sure that exactly where does the fluctuation, which fluctuations do we care about? It's actually not the fluctuations of this light, because this light drives the common mode, and it really turns to the laser. And then it's really these fluctuations that we should care about. it turns out if we want to inject squeezing, it is actually these ports that we should talk about injecting squeezing. Let's then look at the dynamics of the interferometer once more. Basically, we have amplitude quadrature and phase quadrature light coming in, and then these will superimpose with the carrier light. Then this E1 would become amplitude fluctuation, and then this is a force acting on the mirror. And this E2 would just be a phase modulation. So now if the mirror moves under gravitational waves and also driven by the amplitude fluctuation of this light, then that motion also modulates the carrier and then create more phase fluctuation. Then the picture at the outgoing field is like this. So the outgoing amplitude modulation is the same. The output phase modulation is the input phase modulation superimposed with the square root of the power times the motion of the mirror, which contains gravitational wave induced motion and amplitude modulation driven motion. And this driven because there's the m omega squared is a response of a free mass. So, and now let's think about how can we do squeezing? How can we use squeezing to help? Well, squeezing, certainly if you squeeze the phase noise, that's going to be interesting if your phase noise is the dominant noise, as in the first generation of detectors, and that is the case right now. So if you do squeeze, this one, you actually make this one bigger. It doesn't help you beat the standard quantum limit, it turns out, because the products of the two is still the same, but it actually helps you improve your noise at high frequencies, it turns out. But you can actually think about it a little more because squeezing works in all different ways. So what happens if you take this particular combination and then you say, well, I go to the input port, I find out exactly which combination it is, and let me squeeze that particular combination and anti-squeeze the other one, but I don't care about the other one. Then you can improve your interferometer sensitivity. But the problem is, because the coupling here is frequency dependent, you can only help this at one frequency. So it's a narrowband improvement. But if you can figure out a way to do a frequency-dependent combination of the squeezing, you can improve the sensitivity globally at all frequencies, and that surpasses standard quantum limit. So the other way is even more dramatic, which is because we have talked about doing a Homodyne detection, but then what if you do a Homodyne detection at a different quadrature at the output port? And that will basically means you project the outgoing field onto this direction, and then you sum everything up. But during this process, if you make these angles just right so that this actually cancels with that, because they're all driven coherently by the same thing, then you're going to only be left with the signal and this shot noise contribution, and you won't have any back action. But of course, because this coupling is frequency dependent, you have to figure out a way to do this Homodyne detection in a frequency dependent way. But then you can do evading quantum back action. So these frequency dependent squeezing and frequency dependent Homodyne detection, combination, this frequency dependent Homodyne detection are the key, or theoretically are ways to enhance your quantum sensitivity without limit. But of course, in reality, you're going to be limited by your optical loss and optical power. So it turns out there are ways to achieve the frequency-dependent squeezing and the frequency-dependent Homodyne detection. So basically, what you do is you use filter cavities in here, and these filter cavities would actually allow you to rotate the quadrature the squeezing is in, and then to rotate the Homodyne detection angle. And these are cavities that are detuned from your carrier frequency in just the right way. So I won't go into much details about this, but let me show, I'll skip something, but let me show the progress, the gradual progress of squeezing in the gravitational wave community. So basically, I think roughly 10 years ago, the community started trying to get squeezing enhancement in the gravitational wave frequency band. So because previously the squeezing all happens at all very high frequencies, and normally people didn't care about sub-kilohertz frequency band. But within the past decade, there have been a lot of progress. For example, starting from the 2004, there's the first demonstration of sub-kilohertz squeezing, and then followed up by injection squeezing at the Caltech 40-meter lab. And then a few years ago, in the GO600 interferometer, which is 600-meter long, they have demonstrated 3.5 dB squeezing improvement of sensitivity. And then also recently in LIGO detector, there has been a 2 dB improvement of sensitivity. And actually this improvement, it is actually the improvement beyond the previously best sensitivity for gravitational wave detection. So therefore, it's very significant. So the fact is that if people think about why there's only 2 dB squeezing, what they found out is that because the total loss of the optical path from the injecting of the squeezing to the entering the interferometer, and then coming out and to the photodetector and being detected, there's 50 to 60% of loss that is being estimated. And therefore, you can only use 2 dB squeezing because most of your quantum coherence is gone. You're mixing with other ordinary vacuum. You're not squeezed. But the calculation shows that the current design of advanced LIGO probably has 20% of loss. And therefore, in principle, there can be 6 dB of improvement in just advanced LIGO, which is being constructed. And in the future, well, the aim of the community then would be that to get less than 2 dB, 2% loss, and then to be able to use 10 dB and above squeezing. So that's the future plan. But here, I think the summary for ground-based detection improvement is that optical loss seems to be a quite big issue for improving sensitivity using squeezing and quantum improvements. So, and let me mention the constraints of gravitational wave detection on the ground. So basically, I think it summarized there are basically 2 issues. One thing is how do you actually hold your test mass? If you have a suspension system, then if you have a pendulum, then if you want to detect below 1 hertz signals, how long does your pendulum has to be? And the thermal noise in the pendulum seem to be a big problem. And that one, the 2 possible fixes are basically using atom interferometers. Well, people are basically saying you can juggle your mirrors, but then you can juggle your atoms. Basically, you can use atom clouds, which you throw as the test masses, and that's maybe one possibility. And the other one is to use a torsional system, where you use 2 bars that are suspended by a wire, and this restoring force is torsion. And in that case, you might circumvent some of the suspension noise. But neither scheme shows a lot of, well, this one, the atom interferometry, is a new kind of recent proposal, and then you can go to space, et cetera, and then further improve your sensitivity. But this torsional system is not clear how low you can go and how good the sensitivity is eventually can be. And the other problem in the Earth is that you have the so-called gravity gradient noise, which is the motion of material on the ground causing fluctuation in the Newtonian gravitational field. And that field also mimics gravitational wave. And that is fairly difficult to deal with. So therefore, you probably want to go to space, because in space, you don't necessarily have to suspend so well. And then in space, you may have less Newtonian noise like this. So, and that's I guess, the motivation. And when we really think about going to space, we will have to think about interferometer with long arms, because in the space, we're not like in the Earth constrained by a few kilometers of length. We can go as long as possible. Then we have to think about exactly how long we have to go, and how do we calculate our interferometer sensitivity, in such a situation. So it turns out, if we return to this plane wave picture, we have the metric plus the 2 polarizations of the wave. If you want to calculate the sensitivity of the wave, a phase modulation of an electromagnetic wave modulated by the gravitational wave, we have to solve a wave equation that is like this. A wave equation for the scalar, let's just use the scalar wave for the EM wave. And then this metric is the gravitational wave, contains the gravitational wave. So after some calculation, what comes out is basically the following. You can find out that along the unperturbed ray direction of your optical field, you have an additional phase shift due to the gravitational wave. So this is what this equation means. This k vector is the previous k vector of the wave, and this h is the gravitational wave. So it basically phase modulates your electromagnetic wave, but you have to have you have to dot the direction of the wave propagation, electromagnetic wave propagation into the gravitational wave tensor. And this is the formula for prescription for calculating the phase shift. And then if you actually do the calculation, what you find is that just for the z direction propagating wave, for the plus and cross polarizations, the phase shift has two parts. The first part is easy. It's just h times L times polarization tensor dotted into the EM wave propagation direction. That's the same as in low frequencies. But then you have this other phase factor that is due to the wave propagation effect. So just to summarize what happens, let's plot this plot. So let's say that the wave is propagating along the z direction, gravitational wave is along the z direction, and our light along k, and there's a theta angle between the k and the gravitational wave direction. So if k is along the x direction, theta is pi over 2, that's just like our previous Michelson interferometer case, which is previously the strongest signal situation. In that case, we have this blue curve that shows the signal decay. So basically, when a frequency is higher, it decays. And then the typical scale at which the sensitivity decays is when omega L is equal to 1. So it means that when the length of your arm is comparable to gravitational wavelength, the signal starts to decay. So you don't gain signal anymore. So basically, at the beginning, when you increase your arm length, you gain more signal, but then gradually, you don't gain anymore, then you start to lose signal. So, but then at different angles, when k is at different angles, there's actually different 0 points of suppression. Therefore, the situation is a little bit complicated, but the point is, when the frequency becomes higher, when omega L is comparable to 1, things starts to become not as good. So the optimal wavelength, if you want to detect gravitational waves, if you want to use enhancement very well, seems to be when omega L is equal to 1. So now let's start thinking about how interferometry works in this picture. So if you think about it, we didn't talk about how the masses are affected in this new gauge. It turns out in this new coordinate system, the light phase is modulated, but then the test masses are not affected by gravitational waves. So you only need to account for, apparently you only need to account for, you can say that my test masses are fixed here, and then when light, this is the space view. So I have A, I send light to B, and B comes back. I send light to C, light comes back. Maybe that's it. So in the space-time picture, I have this A coming, the light going to B and coming back, and coming to C, coming back. I compare the phase here, and then I can obtain the phase shift, which will, here I do the calculation just using my integrals, phase modulation due to gravitational waves. I can get my sensitivity. But of course, the problem is the test masses are not affected by gravitational waves, but they're still affected by the noisy forces. So what happens is, in this new coordinate system, you have to calculate the following way. So these A and B's, they are not affected by gravitational waves, but their motions will be just noisy motions due to random forces acting on the test masses. And then you basically get your signal, but then you also have local displacement noise, and you have shot noise when you combine the signals. So now, because you have these local noises, so the optimal way, of course, in space, if you want to get better sensitivity, is still to increase your arm length, because the longer the arm you get, the larger the signal you get, and the local motion affects you relatively less. So if you want to avoid the noise from local disturbances, you better have arm length as long as possible in such a way that your arm length is comparable to the reduced wavelength of the gravitational wave. So, because then the signal doesn't get amplified anymore, as our integral shows. So that means, if your frequency is 10 millihertz, where the supermassive black hole signals are, you better have reduced wavelengths of 5 million kilometers. But then, if your telescope is limited with an aperture of 0.5 meters, then apparently the problem is, after 5 million kilometers, if your wavelength is 1 micron, you have a beam spot size of 12.5 kilometers. And then only a very tiny fraction of light is received by B. So what is the consequence of this? Or you can say that I have more money, so I can build bigger mirrors. Of course, that is better. But you can reduce your length. But then the question is, are you able to trade off your acceleration noise so that reducing the length doesn't hurt you? So it's a little tricky problem. So as it turns out, the exercise has been done for LISA, the laser interferometer space antenna, and exactly they got the 5 million kilometers exactly. So the point is, it turns out, I think, if I were to guess, what happened is that probably they did this, they calculated the shot noise, then they set the requirement of accelerator noise to exactly just fit where the knee of the rising, I don't know, maybe people know here. So right, you have the frequency, your shot noise has this frequency, then it rises up at the, when the frequency of the gravitational wave is comparable to the 1 over the length of your arm. And then basically you could just set your acceleration noise requirement in such a way that you just have a valley there at 10 millihertz. So that turns out to be the LISA noise budget. But let me go a little more about how such an interferometer works. So because of the issue that we have this 0.5 meter aperture and then 12.5 kilometer beam, the light is very weak. If you want to have a mirror reflect it and send it back, you get another reduction of signal. So what happens in LISA is that there's no mirrors and interferometer in the usual sense. What is done is that light is detected. Basically, lasers are sent between spacecraft, and then the light is detected right there compared with the local laser. And then the interferometer signal is formed synthetically. And then the exact way to do this, and the other problem is the arm lengths are not exactly equal. So you don't normally do you can't do the usual Michelson interferometer because the usual Michelson doesn't have the right cancellation of the noise. So the interesting trick here is the so-called time delay interferometry, invented by Armstrong, Estabrook, and Tinto, and these guys are at the JPL. So basically, if you have 3 arms that is unequal in general, so what the naive view here is that you have 3 clocks, and then you send signals to neighboring clocks, and you compare the clocks, and then you make up 6 channels because you have 6 links of signals. And the 6 channels, and you have 3 clock noises in terms of how many linear algebra dimensions you have. And when you subtract these, you have 3 noise-free channels. And these 3 channels are the channels where you cancel the laser noise. So one way to illustrate this is to show that, for example, you have the 1, 2, 3, and then you send signal from 2 to 1, and then you send it back. So basically what you do is you take the arrival time here minus the arrival time here. You take this time minus the other time. So at the end, the clock reading in here is canceled, but then you're left with the clock here and the clock here of the spacecraft 2. On the other hand, if you do the same thing with the 3, but then if you try to cancel this one and that one, they're not obtained at the same time. So you're not canceling your noise at the same time. So the trick is to do more such combinations and try to figure out ways to cancel out the noise. And the one way here is that you continue to propagate here, and then you propagate back here, and then you take this one, you propagate here, and then you propagate back here. So for this more complicated loop in the space-time diagram, what you find out is that if you combine all these arrival times, you can subtract all the clock noises, and then you have gravitational wave signals remaining. And then you work out all these kind of combinations, and these are called time delay interferometry combinations that can actually cancel noise without having to interfere, and without having to send light back and forth and interfere, and without without having to send back and forth. You just calculate and then cancel. You still cancel clock noise. So this is a special feature of LISA. Of course, in reality, what happens is not that simple. You don't have a dot with a clock and compare just the clocks. What happens is on each spacecraft, you have 2 test masses, and you have 2 lasers. So with respect to the previous picture, you're adding 6 additional links because you have 2 more signals on each spacecraft, but you have 3 additional channels of laser noise, and you have 3 additional test mass degrees of freedom, and then you cancel this, and then basically it still works out in the counting sense. But the details are complicated for me. So, and then as I said, if we look at LISA noise spectrum, the point is that if we here is a sharp noise, and here it rises up because the sensitivity becomes no good at high gravitational wave frequencies, and here is acceleration noise, and the problem is here, if you move to a shorter arm, you can move away this knee, you collect more signal, you collect more light, so your sensitivity here becomes better, but then your acceleration noise becomes worse. So the total noise curve shifts this way. If you have a longer arm, your acceleration noise becomes better, but you collect less light, and then these raises up. So basically, if you want to reach a better sensitivity at this hertz, 10 millihertz, this is kind of a local minimum, a local stability point for designing the LISA interferometer. And in this case, as we said, and it's actually fairly easy to argue, I won't go into the details, the fact that you have this, basically the fact that you have this picture of having 0.5 meters and going all the way and expanding to this higher beam, the loss is so high, it turns out just having squeezing and quantum mechanical sensitivity doesn't seem to help you this much in this particular configuration. Of course, there's I guess I won't go into the details, but I think there are potential space missions that are designed beyond LISA, where people think about using Fabry-Perot cavities, etc. But I think the problem is maybe thinking about quantum enhancement of gravitational detection in space doesn't seem to be the same kind of enhancement on the Earth. For example, maybe the enhancement doesn't need to be the same way as in LIGO, where you use squeezing, etc. Maybe it's just different ways. That's sort of my intuitive understanding. So let me summarize my talk. So basically, ground-based and space-based detection for gravitational waves, they really go after different sources. Either it is stellar mass object or supermassive black holes. And ground-based detectors, squeezing improves sensitivity, and quantum mechanics may play a major role in the future. And it turns out, because our detectors are at the standard quantum limit, you may use these experiments to study microscopic quantum mechanics, which I didn't mention, but mention here. So, and the other thing is, in space, gravitational wave detection mostly benefit from the long arm length. And it looks like people would like to sacrifice the collection of light over the actual getting better acceleration noise reduction. And therefore, they seem to have schemes, made-up schemes like LISA, et cetera, which are highly lossy, and it's not clear how quantum mechanics helps. On the other hand, there are proposals of using atom interferometers, as but it's a totally different regime. And then I guess it's good to think about such projects. But there, LISA has been thought about for a long time, and many people have been thinking about it. There are prototype experiments, et cetera. And I think for atom interferometer, there needs to be the effort also to think about all the source of noises, et cetera, and to really get it to the same kind of comprehensive understanding as we do for LISA. So thank you, and this is